cloud. So everything we've talked about so far, everybody, regarding climate change, deals with variables that we can quantify, that we can measure, right? We can certainly measure with a fairly high degree of precision and accuracy what carbon dioxide has done, certainly over the last 60 years, right? The instrumental record. And the same, I think the same can be said with temperature. Obviously, we get a little more blurred in our records as we go back in time, because there we're looking at proxy evidence, ice core evidence, tree rings, pollen records, and so on, right? But the last half a century and beyond, certainly when it comes to temperature, we have a really good sense as to what global climates have done. And that's not hyperbole, and I'm not trying to sort of push any particular point. And what this diagram shows is it starts in 1880 here, and I've updated it through to 2020. So this area here where you see the blue curve and the red curve, that is the instrumental temperature record, right, that we have already talked about. So this is temperature anomaly on the y-axis here in degrees Celsius. And remember, when we looked at the temperature record from about 1900, it was about minus 0.4 degrees below the long-term average. And now we're up here at about 1 degree, right? So that difference there over 100, 120 years is about 1.5 degrees Celsius. Okay, that's really, really critical, right? That is the best current understanding of how climate and temperature has changed historically over the last 120 years, right? What I've done here from 1980 onwards is I've just changed the color of the instrumental record just to show, the last 40 years in just a slightly different look, just to give you the sense that that slope there for the red data is a little steeper than the slope there for the blue data. Any questions on that? Does that all make sense? So that's the instrumental temperature record. Now we come to the area of climate change that, quite frankly, and let's just be really honest here, gets a bit more complicated, right? And that is what happens now from 2020 stretching out through to the end of the century, where is climate change going to be by 2050, right? So the reason I say that becomes more complicated is now we move into the realm of predicting what global temperatures will be in 2100 or at a particular moment on the timescale. And of course, we won't know what global temperatures will be in 2100 until we get to 2100, right? I won't be here for sure. So how do we do that? Well, we have to take our understanding of the atmosphere, okay, and build predictive models, right? And a lot of people, as soon as you mention the word model, they go, well, that's just a computer guess, garbage in, garbage out. We can manipulate models to give us the answer. Well, of course we can. But the fact of the matter is that the climate community, the scientific community, just like the computer models we use to predict the weather, have constructed over the last 3 to 4 decades, especially as computing power has increased tremendously and our observations of the atmosphere have increased, especially with regard to satellite records, have built independently around different meteorologic stations in the world, some in Europe, Russia has one, Australia, the United States uses several, a series of climate models, building in the atmosphere, the ocean, and all based on fundamental scientific equations on how the atmosphere works. And you run these models through iterations, right? You run them out and you ask them to simulate, it takes a huge amount of computing time, to simulate what the global climate is likely to do in the next 80 years. Okay, and so what this diagram shows here, and I'll just highlight this here, this pink triangle, right, this little wedge here, shows the range of possible outcomes of global temperatures currently from the climate models. In other words, some of them put global climate change down here at very little, right? So in other words, they're suggesting that global climates might do something like that. Others put the global climate change somewhere up here, right? Now just look at the scale here. This is a 5 degrees Celsius change. That's catastrophic globally around the world. There's no doubt about that, right? The consensus is that most of the climate models really do agree quite strongly that what we are looking at by the end of the century here is about, if we're up here at a 1 degree, we're looking at about another 1.5 to maybe 2 degrees Celsius warming, right? Let me just change the color here so you can see this. So that there is the current scientific consensus about where global climates are likely to be. Okay, probably will be another 2 degrees Celsius warming over the next 80 years. Folks, of course, that depends a lot on the scenarios of carbon emissions and other greenhouse gases, right? If we suddenly stopped all greenhouse gas emissions now, you know, likely global climates will stabilize and may actually come back down towards very little change. If we suddenly double our carbon emissions, then that's going to change these predictions. Does that make sense, what's going on here? So these are the projections showing global climate models. And I think the bottom line take-home message for us here is that we are probably, okay, and that's a statistical statement, we are probably going to see about another 2 degrees Celsius warming by the end of the century. And almost all of the discussions around global carbon and a global agreement, and that meeting will take place in Glasgow a little later this year, is how do we keep global warming underneath this 2 degrees Celsius limit, right? Because if you think back to when we first got together and I was talking about those planetary boundaries, as human impact has gone up, what happens? Does this magical 2 degrees, there's nothing magic about it, but does this 2 degrees Celsius climate change mean that we will move the planet into some other, you know, realm, the so-called tipping points? Does that make sense to everybody? Okay. Any questions on that, on where global warming is likely to be? All good? All right, cool. Okay, so let me end here on climate change with a couple of things. Let me talk about observations and impact. What are we seeing? What are we witnessing? Are there things that we currently can see that, and I will never use the terms prove or disprove global warming, right? Because if we go back to a discussion and little conversation on the scientific method, we're not trying to prove anything here. Or do we have observations and impacts that are consistent and support this hypothesis, right? That we are impacting the climate and that we are moving our global temperature into a rather difficult phase. And, you know, can the Earth come back from that, right? So this is, what do we see on the ground that supports global climate change? Well, here's one. And folks, this could be a very long lecture because there's a lot of evidence. And my goal here is to just to give you a sense, right? To give you a snapshot of some of the major issues that we see scientists talking about here in terms of global climate change. So one is wildfires, right? Incidentally, this is kind of quite relevant to what happened to me yesterday. I was working yesterday right up in the northeastern corner of Oklahoma, Kansas, and Missouri. And it was really, really hazy. And I was like, oh, I wonder why it's so hazy. So I looked on one of the meteorology sites, and it turns out that northeastern Oklahoma was sitting in an area of smoke coming down from the Bootleg fire, right, in Oregon, right? So we see wildfires as a kind of constant threat or constant phenomenon in the media around the world. Obviously, a couple of years ago, the great Australian wildfires, but we see that out west. So this is the US, right? This is kind of a summary infographic of wildfires, and there are various ways to look at this. But what I've done here is I've taken the data from the National Interagency Fire Center and plotted the average annual acres burned per wildfire by decade. So these are the 1980s all the way up to the 2010s, right? And you can see this is not manipulated data in any way. It's just simply saying that the average area of acres burned is going up, right, over the last 4 decades. I'm not suggesting that there is a direct one-to-one causation between the areas burned and global temperatures, but it is consistent, right? Why would you expect larger? Well, look, before I ask that, look at the average length of the wildfire season, right? In the early 1970s, the wildfire season out west lasted about 5 months. Now it's 7 months, right? So where do wildfires play into this discussion of climate change? Why would I show a graphic like this as an observation and impact that's consistent with climate change. What's the link here, everyone? Do you think? And what are some of the potential pitfalls of just simply laying out wildfire size as quote unquote evidence of climate change? How do wildfires play out into it?
I guess it shows that since it's like hotter outside like in California, for instance, or drier.
Sorry, just lost you there for a second. Can you just say that again?
Oh yeah, well, because like it's hotter, it's also drier, which means that they can last longer. So it just makes the environment more susceptible to prolonging the fire.
Yeah, absolutely. Nicely stated, right? So there's an ecosystem sensitivity here, right? If it's hotter and drier, you're going to have, you know, just a potentially a longer period and greater spread of wildfires. Just remember that a lot of these wildfires are natural, right? They're started by lightning, others aren't, okay? But whether they're natural or are anthropogenic in their cause, the bottom line is that the impact in a warmer world will be greater, okay? Yeah, for sure. So that's just one area that you see, you know, you see evidence of. And again, I caution you and caution anybody talking about climate change in if we have one large wildfire to say, there's a large wildfire, that is the direct cause of climate change. Well, we've just got to be cautious there, right? It may or may not be, but in the broader picture, when we're looking at trends, a hotter, warmer world is going to lead to more frequent, larger wildfires. I think intuitively that makes sense, and that's what you've just nicely captured, Cole. They say a picture's worth 1,000 words, right? So this is one that I'm sure you've heard of. In a warmer world, we are going to experience more rapid melting of glaciers. And we are already seeing that, and we've seen that for a number of decades now. So here's 3 examples, and you can go online and Google this and see any number of examples of glacial melt, right? 2 North American one in the bottom here of snapshots. Just look at this panorama in the bottom. This is a glacier in Argentina. So here's 1931. Here where I'm putting red, that's the snout of the glacier. That's the end of the glacier with the little river running into the lake over here. Here we are in 2010. That glacial snout is up there, right? So this one here is, you can see that's the terminus of the glacier in 31. And what we've seen here over 70 to 80 years is a retreat of this mountain glacier, right? And there are examples all over the world. Here's the famous Athabasca Glacier, okay, up in Canada. This was the front of the glacier. This photograph, this is not my photograph, in 1925. This was the snout of the glacier in the early 2010s, right? And that has continued to migrate up the valley here. I showed you this earlier when we first met as an example of one of my slides, and I'll just repeat it here and show you and talk about this in just a little bit more detail. This is this very famous glacial lake in Iceland. This is Jökulsárlón Glacial Lake in Iceland. This is Europe's biggest ice sheet over here, and the glacial lake is right around here on the southeastern corner of Iceland. A lot of people go here. It's one of the kind of go-to places. And I'm standing here on the edge of this lake. Up on the right here is this kind of a iPhone pano. This is the snout of the glacier here. Down here on the left of the photograph, that's the bridge where the lake empties out into the Atlantic Ocean, right? This lake was not here back in the 1940s. And as you can see on the little caption on the top, it's increased its size 4-fold over the last 60 or so years, right? So when we're looking down on top of this glacial lake in Iceland here, right? Here is on the right, here is the snout of the glacier. I'll just put that there in 1991, okay? And if you would just sort of draw that here, the snout of the glacier would look something like that. And there it is in 2006. And on the left-hand side here, so here's that bridge right there, right? And there is the snout of the glacier in, at the turn of the century, 1900, okay? And here is the top of the glacier in 2016 in red, okay? So, this is not fake news. It's not rocket science. It's just a simple physical explanation on that as global temperatures have gone up, as things have warmed, we're seeing this glacial retreat, right, of land-based glaciers. These ice masses are beginning to shrink. And you may think, well, this isn't, terribly important in the big picture of things. But for parts of the world that rely on not just things like glaciers for tourism, but glacial meltwater and a sustained glacial meltwater for their fresh water needs, as many communities in the Himalayas, for example, do, then that has real long-term implications. I don't know if any of you have been to Iceland. I would highly recommend it. Absolutely awesome place. Okay, what is some of the other things, right? What else do we look at here? So this also relates to ice melt, but on a much different scale, right? We're still waiting for the 2020 data to come out on this. But what I've plotted here, again, just to re-emphasize the point, I'm going to look at this in two ways here. So this is Greenland, right? And this is the total melt area of Greenland. So the Greenland ice sheet is in many ways a living, breathing thing, right? It melts naturally in the summer and it refreezes, and it melts and it refreezes. And what we've plotted here from 1979 is the total melt area in millions of square kilometers, right? So in 1979, the melt area, where you could map from satellites looking at where the ice retreated and then rebuilt itself during the winter, was sort of 4 to 4.5 million square kilometers. And with considerable variability, now here we are over the last decade, the melt area is somewhere between 20 to 30 million square kilometers, right? The extent, the aerial extent of the ice melt in Greenland has gone up and now seems to be sort of averaging right out at this 20 or so million square kilometers, right? So what we're seeing is the dumping in of glacial water or fresh water into the northern Atlantic. Why is that important? Why would we worry about Greenland ice getting into the northern Atlantic? Well, here's one of the most significant impacts, I think, of melting ice in Greenland as an example, and what this might do for global climates, right? So this diagram and a long detailed explanation and discussion of global climate certainly goes beyond the scope of this course, everybody, but I just want to give you make the link between increasing global temperatures, melting ice, and what this might do for climates, okay? When you look at, let's say you look at a city like, and I'm just going to roughly plot where this is. Let's say you look at a city like, not quite there, but Winnipeg in Manitoba in Canada, right? And London, more or less, okay? There are two cities there on a similar line of latitude, but obviously they have very different climates, right? Because this one is right in the center of the continent and its climate isn't really impacted or moderated by ocean temperatures. Whereas most of Western Europe, in particular, Ireland, the United Kingdom, certainly to some extent Iceland, and all along Scandinavia over here from Denmark all the way up to Norway and Sweden, their climates there are tremendously impacted and modified by warm ocean currents, right? In the red here. So the arrows here show an average, a diagram of the average oceanic circulation. Obviously the currents are more complex and there's local currents. The red ones show warm surface currents. The blue ones show cold, deeper currents, right? Remember everybody, when we talked about climate, the input minus the output, and the fact that the tropics are permanently warm and the polar regions are permanently cold. And I said, why do the tropics not boil over? Because they send out these warm ocean currents and the poles send back the cold currents. Now, of course, it's very complicated by how the land masses are arranged. But this current here that shifts warm water out of the tropics in the Atlantic is known as the North Atlantic Drift, the NAD. When that current is very close to the US here, it's called the Gulf Stream, right? So the big arrows here are the big long-term average movement of surface and subsurface current, warm and cold current. My point simply is that this warm current called the North Atlantic Drift, right, all of this warm water, keeps Western Europe climates much milder than they otherwise would be, okay? What would happen in the computer model, now this, don't get me wrong, this is not going to happen overnight, right? But what would happen if Greenland continued to melt, right? If we went through a long-term warming in the next 80 years. And that extent of the Greenland ice melt kept increasing. In other words, what would happen if we would continue to dump this cold glacial meltwater into the Northern Atlantic? The computer models suggest that there is a real risk of shutting off this warm conveyor belt, right? Of really dampening and shutting down the North Atlantic drift, okay? In other words, the current would do that and then probably just wrap itself around and come here. That would dramatically change the climates of Western Europe. Again, this is not something that will happen overnight, but it is something that is potentially a long-term concern, okay? Folks, why do we worry about melting glaciers other than water supply? What's one of the key things that you hear in the discussion of climate change as it relates to melting glaciers? What's the big impact, do you think? Besides shutting off conveyor belts.
Isn't it that as the glaciers really recede, that's more of the surface that's exposed that absorbs more heat and it just continues the cycle?
Okay, so that's an interesting point, Matt. So there is a microclimate or even a regional climate impact. Yeah, if you're gonna reduce glacial ice, right, you're gonna change the reflectivity, the albedo. Yep, that's a neat. That's not where I was headed, but that's true, and that's an interesting point. So you're gonna have more radiation absorbed. That will, in a sense, are you suggesting that would act as kind of a positive feedback, a bit of a snowball effect there, that you would absorb more energy?
Yeah, that would just keep the cycle continuing, that it wouldn't really get to a point where it would shut off.
Yep. And we don't know what that point is, right? The models can't handle that. And then where does that glacial meltwater go?
That's what they say is the primary going to be the rise in the sea levels, which then would start to encompass the rest of the surface. Yeah.
So here we go, right? So when you talk about glacial melt within the context of global climate change, this is really the big focus, right? Global sea level changes, okay? So when we have melting land-based glaciers, that water ends up in the ocean. So this, again, this is measurable. There's no real debate here. This shows global sea level change from 1880. So the red is historical markers, right? So gauges in the ocean. The blue here is augmented data from satellites. So we can get really, really accurate measurements of global sea level changes from basically spaceborne telemetry, satellites moving down. So sub-centimeter, now getting down to sort of millimeter scale, right? But what's the take-home message here? Okay, we've just got an average here, and this is 50 millimeters. So that's 5 centimeters, okay, right? And there's 2.54 centimeters in an inch if you're an inch person. So that's a couple of inches there. And then this is plus 200, right? So that's 20 centimeters. So what we're looking at here is 200 millimeters. So that's 20 centimeters plus 5 centimeters. That's 25 centimeters of sea level rise over the last century and a half, right? In inches, that's 10 inches of global sea level rise, almost a foot, okay? Is that a big deal or not? 10 inches of sea level rise over the last 120 years. Should we get bent out of shape about sea level rise, or do you think that's overblown? 10 inches in 100 years-ish, something like that.
I think the people living in southern Louisiana would say that's probably a problem.
That's right. No, absolutely. Or the people living on one of the Pacific Island nations, right? Vanuatu or something like that. Or the Maldives, when the average height of your country is 3 feet above sea level, and you're losing about 1 foot in 100 years, you don't have to be a great mathematician to work out if that trend continues. And as the data suggests here, if that trend starts accelerating, right? Where, if you can see this, the 20th century rate of change is 1.7 millimeters per year. The satellite record in blue suggests 3.5 millimeters per year. In the last 5 years, sea level change has gone up by almost 6 millimeters per year. So the indication here is that that's doing that and is probably going to do that, right? Sea level will keep going. So yeah, Matt, your point is well taken. If you're living in an area, I mean, New Orleans is below sea level, right? What is that going to mean for human development? And the fact that in the US, what is it? Something like I don't know, 50 to 75% of the US population lives within an hour of the coast. Now, I wouldn't suggest we buy property here in Fort Worth hoping that we'll have beachfront property within 100 years. Clearly we won't, okay? But for people who are living on the coast and the industries on the coast and the insurance companies that are looking at this, extremely concerned about what this might cost. Again, this is not just some fancy esoteric what if scenario. Sea levels are rising. Of course, just incidentally, everybody, we're talking here about land-based glaciers, right? This is not icebergs that are melting in the ocean. It's kind of like having a glass of water full of ice. When the ice melts, your glass doesn't overflow because that's already been displaced. This is land-based glaciers that we're talking about. Of course, the Arctic is another area, right, that is very controversial in terms of melting ice. So this plot's from 1979, just like Greenland. Now it looks like the trend is going down, but just look at what the axis here. This is the ice extent, the total area of the Arctic ice cap, right? So remember, with our discussion of stratospheric ozone and the circumpolar vortex, the Arctic is sea ice, okay? So this is sea ice sitting in the Arctic, and it shows the Arctic in 1979 at an aerial extent of about 12.5 million square kilometers. And here we are in 2019, we're down to about, 10.5. And when you look at the average minimum extent of the sea ice, so when we just take 1979 to 1983, this period here, and we're looking at just the average minimum, okay? We're at about 7 million square kilometers in the last 5 years. That's below 4.4 million square kilometers. Bottom line is, the Arctic is shrinking. That sea ice is thinning and shrinking. And here's a vertical look, looking down on top of the Arctic. I think I'll keep it in green here, right? This shows the Arctic sea ice extent in September, and this shows September 1982. So this white line is the Arctic extent in September 1982, right? You can see it right over there. And this is 2019, right? This blue in 2019, okay? That's a significant difference. Why should we be concerned? Are there going to be any winners, do you think, by melting the Arctic? And who's losing? Why, so what? We're going to lose some sea ice. What's the concern here? Do you think, from an Arctic perspective? Anybody heard of or read anything about what's going on in the Arctic? Anybody know or heard about what they're building here in Iceland and on Greenland here? Deep sea ports. Why are they building deep sea ports there?
Aren't they opening up a new canal?
Yeah.
Shipping?
Yeah, shipping, right? If you want to get goods and oil and things like that and commodities to the Asian markets, where do you currently have to go? From the North Sea? Well, you got to go down to the Panama Canal and cut across there, right? As opposed to, if your Arctic is beginning to melt, how about that, right? So it's potentially opening up dramatically new shipping lanes and getting goods and services to other markets. Of course, there's other things going on here as well, everybody. There's all the question of drilling in the Arctic, okay? So that's a massive issue, and who owns those rights, and Russia wanting to drill in the Arctic. And then, of course, if you're an eco person, there's, the habitat and the community and the people who live here, right? The Inuits and the other First Nations people who live here, right? That's their livelihoods, that's their environments. So just a few things that I wanted to make you aware of. Within the climate change discourse, we're talking about wildfires and, melting ice. You'll also hear other things, right? There's a lot of controversy surrounding what will happen to storms and flooding, right? We hear a lot, I hear a lot, that as the world warms, we're going to see more and more hurricanes, for example, making landfall. So we don't see the evidence of that at the moment, right? We don't see any trends yet in terms of the number of hurricanes that are making landfall. But what we are seeing is that there appear to be more large category 3s and 4s developing. All right, so the idea here is that if global temperatures increase by another 2 degrees Celsius worldwide, we are going to see an intensification of storm systems like hurricanes. Why is that a big deal? Right? Well, that's a big deal if you have 4,000 drill rigs in the Gulf of Mexico, right? Or flooding from hurricanes making landfall. So that's also a major concern. All right, so let me wrap this up. Let's wrap up global climate change. So what do we do? Okay, if we just take a step back, and I hope you have a better sense as to some of the kind of, not just rhetoric, but the discourse around this notion of climate change and global warming, and some of the things that we know and some of the things that we're less certain of. I think there really is now a growing and solid consensus that climate is changing, and humans are having a significant role. In many parts of the world, and I think honestly, to some extent in the US, that it's still partisan and it's polarizing and it's controversial. But the conversation is really moving beyond whether climate change is occurring. It's now, what do we do about it, right? Do we do nothing? Do we just sort of roll the dice, in a sense, which is why I've got this graphic? Do we do nothing and wait and see before we implement any kind of draconian policies about changing our fossil fuel use and cutting back on carbon until there really is something catastrophic, and then do something about it? Of course, many people argue at that point it'll be far too late, right? We'll already be committed to a warmer world. Or do we start making changes now and adapting to it as quickly as we can? So that's also part of this, conversation. I made a comment that, so I get this frequently, right? And I think I've made this comment a couple of times. It really happens to me a lot, right? I get asked, do you believe in this global warming thing? Whether I'm sitting at Starbucks or sitting on a plane or at a dinner party, whatever the case may be. So I don't want to oversimplify this, but I'm going to give you this is my kind of 30-second elevator pitch, right? As I've said before, everyone, it's very tempting to remember the two boxes, right? If you're sitting in the global warming quote unquote believers, and I hate that term because it makes you think that it's some sort of faith-based construct. But if you are in that box, it's very tempting to say, well, of course I believe in it, okay? Or vice versa, if you're a skeptic, you could probably say, no, I just think it's all a load of baloney made up by the liberal left to make us buy battery-powered cars, whatever argument you're coming at it from. And I often find myself fumbling, about, well, how do I approach this? Do I want to annoy this person? Do I not? Do I, what's the agenda? So, here's my 2 cents. This is not an exam question, and it's absolutely a sort of take it or leave here. But here's where I come from, right? When someone asks me, tell me about global warming, or what's your view of global warming? There's really 3 things that I just touch on, right? I say, so here's number 1. Okay? We've known for a very long time that there are gases in the atmosphere like carbon dioxide that prevent Earth's heat from escaping, right? We would be a frozen ball without these gases, right? That is the greenhouse effect. Okay? Point number 1, not up for debate. We've known that for 2 centuries. We also know from direct measurements, right, that emissions from human activities, whether it's deforestation or burning, gasoline in vehicles, generating electricity from coal-fired power plants, whatever, that we are thickening the layer of those gases in the atmosphere. Okay? That is quantifiable. We can also measure that. The carbon dioxide, we know that we have increased by about 50% since the Industrial Revolution. And this is simply keeping more heat within our Earth atmosphere system. Right? Our planet is warming. Okay? And finally, that there are observations of things like increasing temperatures, rising sea levels, melting glaciers to confirm this added warming. And I just simply leave it there, right? So the greenhouse effect is real. We are adding to the greenhouse effect, and we are seeing measurable responses in our ecosystems confirming that the world is warming. And then what I want to do is get to, and then I just see what people say, right? Rather than sort of bring out the white dry erase board and a bunch of dry erase markers and give them a lecture on climate change or carbon dioxide or tree ring analysis or anything like that. Most people are like, I'm not interested in that. I just want to, and then I often engage in really interesting conversations about, well, what do we do? the things that we talked about, last time on Tuesday? Is it a carbon tax? Do we need to drastically change the way we live? Or is climate change just simply that something that we're going to live with, and we're going to have to mitigate and adapt to it? There's going to be winners and losers, right? So let me stop there and get your thoughts on that. What are your thoughts? And I'm not suggesting you need to take this down and just repeat my 2 cents worth, but that's my, I find that when I do it that way, to be honest with you, that kind of lowers the temperature of someone who may be coming at this from a particular agenda. I don't know. Does anybody have any other? I know you've shared a little bit about some of your personal anecdotes and some family members that don't believe in climate change, but that's how I approach it. It's just me. Any thoughts or comments, sleepyheads? All good. Okay. What do we do about it, right? Who's to quote unquote blame? Who's the villain in all this? Well, if we're adding these greenhouse gases to the atmosphere, right, then who are the big emitters? Okay. So it's actually quite difficult to get this data. I'm still looking for the last couple of years' data. It may be out and I've just missed it. But this is pretty current. This shows the top 10 emitters of fossil fuels, right, at the moment. So this bottom pie here shows the total amount of carbon dioxide emissions. This is CO2, right, not carbon. Okay, so let me just pull out the calculator here just to make a point. This was 2018. Come on, Mr. Sleepy Calculator. So that's that is 37 billion tons of CO2 divided by 3.67, right? That's 10, right? That is 10 gigatons, 10 billion tons of carbon. Remember the carbon cycle, we said that is about 9.5, right? So it's right in that 9.5 to 10 billion tons of carbon. This is expressed as carbon dioxide. Folks, these circles here are all scaled relative to one another, right? So China is the larger emitter, the largest emitter of carbon dioxide, followed by the US, all right? Followed by India. So these three countries, if we are going to make meaningful inroads into reducing carbon emissions, it is folly to suggest or even think that we'll be able to do that without those three countries leading the way, right? China, India, and the USA. They have to be at the table. We have to be driving the boat when it comes to reducing carbon, if in fact we want to, right? If that's feasible and possible. And what's really interesting, I think, for me, is when you look at this, when you look at the trends of those three big emitters, just look at the US here for a second, right? These are the current contributions from the big three emitters, okay, in terms of the global percentages. So China currently accounts for about 28% of all the emissions of carbon dioxide. But look at the US trends from about 2000, okay? That trend is downwards, right? It's very, I don't know, maybe easy to think of the US as the world's biggest polluter, and B, that everything's going up and up and up. Carbon is down. We are reducing our carbon emissions in the US and have done so successfully for 2 decades. What's driving that, everybody? What is one of the major reasons why we've seen that downward trend in carbon dioxide emission in the US? Do you think? Oh, there's a nice exam question.
The Kyoto Protocol.
Interesting. Why did you say that, Ahmad? Go a little further with that. The Kyoto Protocol.
If the agreement was to lessen CO2 emissions, then I think the US is obliged to the treaty.
Okay, interesting. Yeah, Kyoto Protocol, that was the protocol that was originally put forward and signed in the city of Kyoto in Japan. It went through several iterations, right? It's now called the Paris Accord or the Paris Climate Agreement. I'm glad you said that. So the answer is no, But I'm glad you said that, Ahmad, because the Kyoto Protocol, which was the first attempt for a global agreement to reduce carbon emissions, right? Everyone was on board, and there were two countries that did not sign it. They did not ratify it. And in 1995, the US Senate voted unanimously. There were 5 absentee votes. There were 95 votes, I believe it was, saying the US should not ratify the Kyoto Accord. We did not sign on to it, right? It wasn't legally binding anyway. It was voluntary. But does anybody know why, the primary reason why the US back here in 1995 did not sign the Kyoto Protocol? Any ideas why we said, I don't think so? Because there were 2 primary countries that were exempt. And you know what those countries were? China and India, right? And so the US Congress, the Senate, and the Clinton administration said that puts us at a massive disadvantage to say that we're going to reduce our carbon footprint. We're going to have to either put in all of this expensive technology or go through a dramatic change in our economic driver, right, which is fossil fuels. And that puts us at a huge disadvantage relative to these other countries. So I'm glad you said that. So this reduction was not due to the Kyoto Protocol, right? It was largely due to what? Reducing carbon. What has been our single biggest reason why we've reduced CO2, do you think?
Has it been the influx of renewable technology?
That's one of them. Yeah. Renewables going from basically less than 1% of our electricity generation here in 2000 to where we currently are at, 10%, 7 to 10%, somewhere in there. And also, even more significant is what? Think energy, folks. Come on, we've done this.
Is it the switch to natural gas?
Absolutely. Yeah, nice, Irada. That's the switch to natural gas. 50% coal, 23% coal, right? That's had an enormous impact on our carbon footprint. On the other hand, this here from 2000 in China, what has driven that peak in carbon emissions? And India. That's all on the back of coal, essentially, right? So my point simply here, I think, is whilst it's very easy perhaps to kind of lay the blame on big industry and the United States and so on. I mean, I think the market is driving the reduction in our carbon emissions, and many people would argue, therefore, that perhaps we shouldn't be thinking about a carbon tax. We should be thinking about efficiencies and newer technologies. But what happens to the global climate whilst these other countries are 20, 30, 40 years behind us, right? That works well for the United States. But even though China has President Xi has said that China will be carbon neutral by 2060, we've still got 40 more years of burning coal to get there, right? So it's complicated. And I've shown you this one before, okay? So that's just a repeat saying 2020, the carbon emissions look like they're going to be down. Okay, all right. Before we take our break, let me end on this diagram, okay? I just want to take 5 minutes to end here because this is a really interesting, I think, concept. And I want to end on this note of, what can we do? What is our potential outlook for reducing carbon emissions, right? So in 2003, a paper comes out by a group of scientists that suggests it's a really kind of it really got people's attention, that showed a possible path forward to reducing carbon, and it was called carbon stabilization. Okay, and all this simply is this is it looks like a very complicated diagram, but all this simply is showing potential pathways to reducing carbon. That's all it shows, right? So we've got year on the bottom here. This red line here is 2005, okay, because the paper comes out in 2003, and they say, let's look at what's going on from 2005 through to 2055. The paper here, this research, was looking at what can we do over the next half a century, over the next 50 years, right? So first thing to look at, this scale here is carbon in billions of tons per year. And these are the historical emissions, right? So these are the historical emissions. And I'm just going to circle that there. That was 2005, right? There we were in 2005. Those are our historical emissions of carbon, okay? At about 8 billion tons of carbon, right? They then said, so here we are in 2005. They then said, we've got one of two pathways we can go. We can either keep going along the business as usual, the current pathway, which is that one, or how can we just suddenly keep our carbon emissions in 2005, which were 8 billion tons per year? How do we get to 2055 in 50 years' time and still have our global carbon emissions at 8 billion tons per year? Does everybody see that? So picture yourself in 2005, and you're saying we've got these two scenarios going out. One is in 50 years' time, we're still at 8, or in 50 years' time, we're at 16, right? And this green triangle here is known as the stabilization triangle, right? It's the carbon stabilization triangle. And in fact, it is not made up of one little wedge, one triangle. It is broken down here into 8, right? I've just kind of drawn this here for 5, 6, 7. There are 8 little wedges that make up this stabilization triangle. And here's the bottom line, everybody. Each one of these wedges is an emissions strategy to reduce carbon by 1 billion tons per year, right? I'll say that again. Each one of these little triangles or wedges is a carbon reduction strategy of 1 billion tons per year, okay? And they laid out in this scenario 15 technologies that we already have, 15 things that we have. This is not some, you know, magical technology that doesn't exist. For example, in one of the wedges, okay, they say if we were to, in 2005, if we were to ramp up wind power by a factor of 30, in other words, in the next 50 years, we have 30 times more wind on the ground, okay? That should reduce the amount of carbon by 1 billion tons per year, right? So you can scale up wind by a factor of 30. Or we can double the miles per gallon in our vehicles from 30 to 60. Or we can scale up biofuels by a factor of 30. Or we can build another 300 nuclear power plants, right? The point here, everybody, is not to learn these 15 strategies at all. It's just to understand or appreciate that we actually have the technologies at our fingertips to reduce carbon dramatically, right? You can see in the US, we're ramping wind up and we're converting coal-fired into natural gas. That is, in a sense, taking out one of these wedges, right? So when you look at, when the paper comes out in 2005, and then you fast forward here to 2020, what path are we on? We're still on the current path, right? We haven't made any inroads yet. We're still ramping that up to there, okay? What is the likelihood that we're gonna do that and then suddenly do that back to 2050? Yeah, tricky. Does that make sense to everybody, what this diagram shows, the stabilization wedges? It's a really interesting, I think, was a very important contribution to be thinking about, you know, the technologies are there. The question, and it's not easy, right? I'm not for a moment suggesting it's easy, because as some of you have commented on before, you've got to start thinking about the question of scale here, right? And each one of these technologies comes with, you know, problems. So yeah, the reason I asked you about biofuels in the exam, if we're going to scale up biofuels by a factor of 30, that sounds great, okay? But where's the land? How about feeding people or scaling up wind by a factor of 30? Where do we build the transmission? Who gets to pay for it, right? So it's not easy. And in fact, I think the authors of this paper had a really nice little catchphrase. They said, what we're trying to do here with global climate change is we're trying to solve a monumental problem by introducing a bunch of heroic steps. And the world is just very, very slow, I think, at the moment in implementing these heroic steps. It just simply is not easy, right? So that's my kind of take on a complicated topic that deserves an entire course on its own. But I'll stop there. Let me see if there are any comments, thoughts, or questions before we kind of put a wrap to climate change and then take a break and come back and talk about freeze. Any thoughts or comments or questions, everybody, on what we've covered so far in climate change? I hope that has kind of just opened up this box of complexity to you all. Thoughts? Nada. All quiet on the Western Front. Okay. All right. Okay, let me start this section in chapter 7 just with a question. How many of you have had the opportunity to walk through and kind of be immersed in a tropical rainforest? How many of you have been through these ecosystems? You get a sense of who's done that. Anyone? No one's been in a tropical rainforest. Okay. So this photograph here is one that I always like to start this kind of conversation on deforestation with, because it's a spot that we always stop at with our students when we go to Costa Rica on the study abroad program. And we are driving up here, ultimately headed to this area that is right kind of in the top right-hand corner of the photo here. Okay, this is, I don't know if I can spell it out here, but you'll see it in the book. This is the famous Monteverde cloud forest in Costa Rica, right in the central part of the country along one of the kind of volcanic ridges. And it is a tropical rainforest, but it's at an elevation that keeps it certainly not permanently in the clouds, but it spends a lot of its time in the clouds. And we stop here because even though this is a sort of long, bumpy drive ultimately to get there, I really like our students to just see and appreciate two possible scenarios here for this landscape, right? One of the scenarios you see in the foreground here, okay? And certainly these patches all the way going up these mountainsides over here, right? Areas of tropical forest that have been cleared. You also see patches up on the side of the mountains here, right? So areas of forest that have been cleared, deforested. In this part of the world, almost exclusively for grazing, right? And I don't know if you can make it out on the photo. I don't know how clear it is on your screens, but if you look in the foreground here pretty carefully, you might pick up the fact that there are these terraces, right? It looks like there's these little sort of ridges on the landscapes here as the cows have gone and sheep have gone up and down to graze in these pasture lands. And when it rains, what we find is a lot of runoff and erosion and sediment gets into the rivers in the bottom of the valley here. That's one kind of end of the spectrum. And then what we do is we get back in the bus and we drive all the way around to the top here. And the second one is when we get into this undisturbed tropical forest, right? Untouched, never been cleared, never been cut down. And incidentally, that's the distinction we make between primary and secondary forest. Primary forest is forest that has never been impacted by humans. Secondary forest is a forest that has regrown after deforestation, right? And if none of you have been through a rainforest or a cloud forest, any kind of tropical forest, I couldn't encourage you hard enough to try and make that journey one day. It is a remarkable experience to walk through these types of ecosystems and to just immerse yourself in the biological diversity, right? It's just an incredible experience. From an environmental perspective, right, this topic, deforestation, remains right at the front, in my opinion, of issues that are destabilizing landscapes. And, you know, I'm not necessarily a fan of top 10 lists or top 5 lists, but if you ask me what are the top 5 environmental issues that we faced, deforestation would be undoubtedly up there, right? The removal of tropical forests, and not just tropical forests. I'll show you a map of forests that we're going to look at, right? But deforestation for a number of reasons, both economic, environmental, ecologic, climate, carbon. It's a really important pressing environmental issue. So that's where we're headed here in terms of the deforestation. Another one of these general maps, it's from a paper a few years ago in the journal Nature, and it's a generalized map that just simply looks at the terrestrial land surface, and we don't have to worry about the details of how they came up with this, but this is kind of a human impact map, right? Levels of disturbance. Anything in green here is essentially undisturbed land, right? Humans have not been in there and disturbed it. So yeah, all right, this is not to imply that we've got a rainforest here. This is clearly not. This is the Sahara Desert, but we've got the central core of the Amazon, right? The outback. There are large, vast areas, obviously the great tundra areas of Russia and Canada and so on, right? So there are areas that remain still relatively undisturbed, okay? But of course, the vast majority of our land, and as you start getting into the reds here, you start seeing enormous disturbance. Clearly, the deforestation of Europe and the conversion of that to agriculture. Obviously, when you look at the US here, right, the eastern third or the eastern half of the United States, in terms of industry, agriculture, urbanization, and so on, right? And South Asia, remember, I come back to the circle that we talked about with population, right? Half the world's population live in this region over here. So we have had an enormous impact on the surface of this planet, and that has played out to a large extent in terms of our conversion of forests and other land into agricultural land. If we look at the average from what satellites are showing of our ice-free area, in other words, if we take out the frozen tundra and if we take out Greenland and so on, about 40% of all of our ice-free area has been transformed into agricultural land alone, right? So that has had an incredible impact. The other thing I'd like to just comment on, and so what we'll do this morning, folks, is I'm going to introduce you to deforestation, and we're going to look at rates of deforestation. And then tomorrow morning, we're going to come back and look at why this is happening. Okay, what are the sort of underlying, you know, socioeconomic reasons for deforestation? So one of the important themes here, or something to think about and contextualize, is that we look at, and I like to refer to forests as system regulators, right? System regulators. What does that mean? That means that forests carry out a whole host of environmental services free of charge. We looked at that a little bit. We talked about that when we looked at instrumental and intrinsic value. Remember that view of the Sarapiquí River in Costa Rica? But system regulators, let me give you 2 examples. So one is the hydrologic cycle, right? When we have an intact, rich, diverse forest canopy, okay, that forest, when you get rainfall falling onto that forest canopy, you know, something like 3/4 of all of that rain gets evaporated and transpired back to the atmosphere, and about 1/4 of it ends up impacting the soil and infiltrating or running off. You've got a much more protected surface here on the left-hand side than when you start clearing trees, right? When you start deforesting and you remove this protective canopy, you kind of reverse that, right? Where only about 25% of the rainfall is returned to the atmosphere through evaporation and transpiration from the vegetation. And you've got a much larger proportion of that rainfall that can then erode surface soils and wash out nutrients and minerals and so on, right? So canopy binds soil, it protects soil, and it circulates the hydrologic cycle. I mean, think about climate, right? Obviously, in terms of photosynthesis and producing oxygen, forests are absolutely critical. So there is a whole host of ecosystem services that forests provide, again, and they do it free of charge. How nice of them. Okay. Everybody with me? Oops. Okay, I'm having a little problem with my computer here at the moment. So that looks reasonable. All right. So let's start with this map, right? This is I think this is the latest, best high resolution image of the world's forests. And it's measured here, everybody. If you just look at the scale at the bottom, this shows canopy height. So as you start getting into the darker and darker colors, at the very end of the spectrum here are canopy heights at about 50 meters, right? So that's about 150 to 170 feet. And the height of the forest canopy obviously is a proxy for the density, the intensity, the diversity, and so on, right? Now, a couple of points here, everybody. One is we're going to talk here, and I do this in the chapter for, I think, good reason, is we're going to focus a lot, and perhaps almost exclusively here, on forests that are in the tropics, right? These are the tropical forests. We often refer to them as the tropical rainforests, okay? And we do that, again, for a couple of good reasons. One is, you know, the tropical forests are the repository of biological diversity. They are by far and away the richest ecosystems. It's where the majority of the world's species exist, and we'll examine why that is when we get to biodiversity in a bit more detail tomorrow, right? But the tropical forests, and here let's just say we're looking at 30 degrees north and south either side, well, not percent, 30 degrees north and south, right? They are geographically the most important, right? They're also the richest, the tallest, the most diverse, the tropical forests. They're also the region that are under the greatest threat, okay? Yeah, we're going to talk about the Amazon in just a second. We're going to talk a little bit about some of the great African forests and what's going on there, okay? And again, if we come back to the fact that a third of the world's, more than half the world's population live inside this circle, what's going on in this part of the world, right? Southeast Asia and Indonesia, hugely problematic. But I have to acknowledge, and I do that here, is that we're going to focus on this area at the expense of other very important regions, right? I'm not implying here for a minute, everybody, that the temperate mid-latitude forests here or the coniferous boreal forests of Canada and Russia are any less significant or important, right? They are important and they are under threat for sure. But when we think of deforestation as an environmental issue, rightly or wrongly, that focus tends to be up in the tropics, and that's what we're going to look at. So let me see if there are any issues there or any questions. Does that make sense? That's where we're focused. Any questions on the map here? All good. Okay. So let's start here. Let's go into the Amazon for a little bit here, right? This is an important diagram. You're going to see this next week in some form. And it's a really important diagram because this is the tropical forest, I suppose, that really got the world's attention and in many ways does. You know, let me make another comment before I go any further, everybody. I'm going to try, you know, there's a risk here when we do deforestation, maybe more so than any other topic or chapter, of bombarding you with statistics, right? Percentage of deforestation rates, square kilometers, hectares, whatever. Yes, it's important to try and get a grasp as to the geographical extent of deforestation, but I'm also going to try and simplify that and give you context. But we have to start in the Amazon. One is because it is such an important repository of biodiversity, right? Often people think about the Amazon as the lungs of the planet, right? In terms of providing oxygen. It's also certainly where some of the most controversial deforestation practices are going on, and it's just very, very well studied. So let's start in the Amazon. I haven't plotted the 2020 data on here for a reason, but I'm going to update you on that, right? So what are we looking at here? Okay, so this shows the Amazon deforestation, right? The annual rates of forest loss in the Amazon. And I need to just make a couple of, make one comment here. We're talking here about the Brazilian Amazon. Okay, so this doesn't include any of the Amazon forest that cuts down into other places like northern Argentina or touches into Ecuador or Colombia. So this is the Brazilian Amazon, and this data comes from a combination of the Brazilian Space Agency and NASA. So these vertical green bars, so these four here, and this doesn't, I mean, I know this suggests that the rates are exactly the same for these years. They're not, but these are the best estimates. The data is problematic from this period. But these vertical green bars relate to this axis here, annual forest loss in square kilometers, right? Annual forest loss in square kilometers. And this red curve coming down here refers to the right-hand axis, right? So what is that referring to? It is the percent of the 1970 cover remaining. So there was a big survey done, both aerially, photographically, early satellites, on an estimate of what the 1970 aerial coverage of the Amazon was, right? It coincided with Earth Day, incidentally. So you can see here, this percentage is about, 93 to 94%, right? Here we are in 2018, we hear at about 83%, something like that. So what is that showing? What is that saying? That is saying that since 1970, if we've got 83% of the Brazilian Amazon remaining, that means we have lost 17% of the Amazon to deforestation, if everybody can see that. All right, so someone talk to me about what you see here. What jumps out at you when you look at, if you just look at the green vertical bars, for example, what jumps out at you in terms of deforestation in the Amazon? What do you notice? What can you say? Come on, young environmentalists. There's been too much silence here in this lecture this morning from you. You're normally more chatty than this. So what are we talking about here in terms of the overall trend of deforestation in the Amazon? What strikes you? Nothing?
I think that it looks like it's going down, but it's
Okay.
going down because there's less rainforest to deforest.
Well, that's an interesting comment. So I can see why you said that. That's a really interesting comment. Was that Cole, right? Yeah. Yeah, interesting comment, Cole. We're going to look at that when it comes to species loss. Are there less rhinos to poach or less elephants to kill? So in this instance, this is just the growth. This is the annual rate. So the answer to that is, for this plot, is no, but that's an interesting take. These are annual rates. If you were probably looking at the total amount of forest loss, then that would be a relevant comment. Yeah, interesting point. So it looks like it's going down. Yeah. What else do you folks notice about the plot here? What strikes you? Take a look at, so this here, I'm just going to point out 2004. So this is 2004. This was a particularly high year in 95, but let's just look at the 21st century, right? We look at the last 20 years here. 2004, this was enormously problematic. The rates going up here from about 10 to 12,000 square kilometers up to 25,000 square kilometers, right? That's a doubling in the rate of deforestation. The causes behind that is what we're going to talk about tomorrow. What's going on here? What's driving deforestation in the Amazon? Because what's driving deforestation in the Amazon is not necessarily driving deforestation in the Congo or in Borneo in Southeast Asia, right? So we have to examine that. But then to your point, Cole, look at this, from 2004, right, to 2012, we see a dramatic decline in Brazilian deforestation, okay? I remember when those 2012 data came out and the world was kind of, absolutely aghast at what was being reported from the Amazon. And again, I know this is kind of a little bit of a dangle out there. We'll look at why that, what are some of the things that happened that put that into place. Okay? But here's the depressing part. The depressing part is that we are seeing this, okay? And even though the 2020 data is still being debated, which is kind of interesting because, the Brazilian government don't want to come out and say, hey, we've doubled our deforestation rate. So there's still some arguments and controversial aspects to the 2020 data. But a paper that came out recently in Nature, in the scientific journal Nature, right, showed that between August 2019 to July 2020, so it's not a calendar year, but for that 1 year period kind of wedged in here, we've got about 11,088 square kilometers, somewhere in here, right? So this trend is doing that. And again, there's a reason for that, right? When we look at the Brazilian Amazon as a whole, okay, so this is what I mean by trying to just give you a context to this. If I was to say to you, the Amazon has lost 718,000 square kilometers, you probably go, okay, how big is that? Well, here's Texas, right? Just to give you a sense of scale, right? Texas is almost 700,000 square kilometers. The Amazon has lost the size of Texas since 1970. I don't know if that helps you kind of picture it or not, okay? But I would argue Texas is a pretty large state, right? The Amazon has lost Texas. And when we talk about deforestation, we do also have to be very clear about, are we talking about deforestation and how does that play out in terms of reforestation somewhere else? Here, this is just total tree loss in the Amazon. That is an extraordinary depletion of biological resources in the Amazon basin. All right. Now, let's look at this in a bit more detail. So what I've taken here is I've taken that first map we looked at, right, of tree canopy height. So you're looking at canopy height here again from that big one. And I've tried to find a way here, everyone, to, when we take these little journeys into the forest here, just to give you a sense of scale and where you are, right? So here's the Amazon. Oh, just incidentally, so here's the Amazon River, right? You can see running through here. But let me point something out here. This area down here is an extraordinarily important ecosystem. We just don't have time to talk about it, but this is known as the Cerrado down here. It's not tropical rainforest, it's a temperate forest, and it has been decimated. The lighter the color here, the more deforestation that you see, right? So this is an ecosystem that has been really, really decimated. Just, everyone talks about the glamorous tropical rainforest. Again, for good reasons, but we do have to acknowledge there's other parts that have been tremendously deforested. So we're going to jump into a little area here called Rondônia, okay, in the Brazilian Amazon. And the reason we're going to go in there is that Rondônia was the area in the 1980s and 1990s that really got people's attention in terms of deforestation, right? So here we are in Rondônia. I need to change the color here because green's probably not going to work. And we're looking at a satellite photo here of a part of Rondônia in 1985, okay? And anything in brown, these light areas that you see, all of these light areas are areas of cleared land, deforested. Obviously, this dark green is intact primary forest, okay? BR, that's a name of a road. And then these are the towns and so on. Rio Jacineparaná is a river. All right, so here's Rondônia in 1985. Now I need someone to talk to me. You're not getting off scot-free here, everybody. What do you see? What do you notice about this image of deforestation in Rondonia in 1985? Who wants to jump in here? And I'm leading to an issue that I'm going to ask you about next week in the exam. Not going to be no hidden thing here. I'm going to ask you to explain this. So what do you see? Come on, people. Let's go. Let's go. What jumps out? Just look at the scale on the bottom left there, 40 kilometers. If I was to give you this image of deforestation in Brazil and say, discuss, what would you say? I think I should have the Jeopardy theme song playing in the background. I've heard from Matt, I've heard from Cole, I've heard from Jacob, I've heard from Ahmad, we've heard from Irada this morning. Who else wants to jump in? Or any of those? What do you notice? Does anything strike you as interesting, odd, peculiar about this deforestation image? Nothing? People? Is there nothing about this part of the image that strikes you as odd or interesting?
I think it's kind of weird how it's like almost little road. It just seems kind of like random spots. It doesn't really seem to be any like rhyme or reason, but it also is kind of like these little lines, but it just looks kind of weird.
Cool. Excellent. Finally. All right, Jane. Look, I'm going to be honest with you. If you open the chapter and you read or glance through a chapter ahead of lecture, you should be jumping on this. Yeah, something looks odd here, Jane. I mean, if I was to say we're going to deforest this area, would you not expect to have like one big gigantic cleared area as opposed to this? It's pretty odd, right? Kind of just looks like a jigsaw puzzle that someone's come in here and picked out a whole bunch of pieces. Okay, it is this is a key term here. This is very fragmented. Okay, is that what you're alluding to, Jane?
Yes.
Yeah. So let's explore that. This is 1985. Here's 10 years later.
Is it something similar to like thinning? Because like my family, like being in East Texas, like the paper mill was big about like having tree farms, and every, so they would plant new trees, but then like every 5 years or so they would come through and they would thin. And so they would take some, but they would leave some to continue to grow. So like, is that what they're going for? Like a thinning almost?
Okay, no, they're not, but that's also kind of an interesting comment. Okay. Yeah, no, but interesting. You'll see why it's interesting a little later, Matt, but thanks for that. So I'll just flick backwards and forwards. Here's 85, oops, here's 94. 85, and I'm just going to circle an area here that you can keep an eye on, right? Let's keep an eye on this area here. Intact primary rainforest, right? '94. Unbelievable. I mean, it's pretty hard to argue with these kind of satellite images, right? 85, 94. Okay, here's the Jane Sundell effect, even greater up here in the top part of this image, right? This bizarre, funky, odd. So what's going on here? So in Brazil, in the Amazon, one of the reasons why this really came to the sort of public's attention was this really strange pattern of deforestation, right? Yeah, there are areas that you're going in and you're taking out big square trunks or large geometric shapes of forest, right? Yeah, we see that up there. I'll just circle one down there. Yeah, we see these areas where patches of forest are coming up. But we also see the dominant pattern here is this, and this is refer to one of two things, right? It's sometimes referred to as the herringbone. Oops, hard to write. The herringbone pattern or the fishbone pattern of deforestation. I don't know if you've heard about that or read about that, but the fishbone and herringbone. So what it looks like, as you can see, right? It looks like the kind of skeleton of a fish, right? You've got this main spine here, and then you've got, you know, it looks like you've taken a nice little tilapia and eaten it and left behind the framework of the fish, right? The fishbone or the herringbone pattern. So
It
why
also
does
looks like horizontal fracking.
Yeah, yeah. Well, it turns out it's not fracking, but I see what you're saying. Like deforestation and fracking combined. So what's going on, right? So this is a form of deforestation that, again, that really got people's attention, and it came about because there were real, and again, we'll get to the, you know, the underlying reasons of deforestation. So the pattern that you see here in Rondonia, for example, is not a logging company going in and clearing out 10,000 football fields in one big square area, right? This pattern, this herringbone pattern or the fishbone pattern, is done by subsistence farmers, shifting agriculturalists, and sometimes that's known as swidden agriculture, right? These are done by small-scale farmers. They don't own the land. They get access into the forest along a road, right? So this here is a road, that there is a road, right? This here is a road, and they get access into the forest along these roads. Often these roads are illegal logging roads, and sometimes they're legal roads, right? Because the forest is an enormous frontier. It's not easy to get in there. But once you have access in there, these small-scale agriculturalists will go in and they will clear a small area of, say, 2 to 5 hectares, something like 10 acres, right, in a little square. And then someone else will come along and do that, and someone else will come along, and they start clearing these small areas sequentially. And then what do? They cut down the trees. So this is a term you may have heard. They slash the trees down. And then what do they do with the trees? They do what to it? They burn them. Anybody heard of slash and burn agriculture? Right? Slash the trees, burn the trees. Why? To get those nutrients in the trees into the soil as quickly as possible. And then they plant cash crops, right? For subsistence. And then 2 or 3 years later, they can't grow anything on there because all the nutrients are gone. Again, that's a mechanism we'll talk about tomorrow. And they go and get another one, and they go and get another one, and they go and clear another one. So these lines that are branching off the main roads here on these sort of spines are shifting swidden agriculturalists, subsistence agriculturalists that are clearing sequentially smaller plots and moving into the forest and clearing forest in that way. Does that make sense? Everybody? Okay. And that mechanism, at least in Rondonia, is a much more destructive form of deforestation than going in and simply taking out one big chunk like that. Why do you think that's the case? Why would that herringbone pattern be more destructive than that? That would make a delightful little short answer question. Why do you think? Or another way to think about this, let's say this is the area that's cleared. And let's say that area that is cleared is 10 square kilometers of cleared forest, deforested area. And let's say inside this box here, all of the brown area that you see, in other words, all of this brown area that's been deforested, let's say that adds up to 10 square kilometers. The amount of forest that's actually been cleared, trees removed, let's assume it's the same here as it is up here, but the one in the top left is much more destructive. Any ideas why that may be the case? Any thoughts?
Professor, could you repeat the question one more time?
Bet, Kylie. So if I was to, if I was to come in here and clear an area like that, let's say that's 10 square kilometers of cleared forest. And let's say this area, I know it looks bigger because I'm drawing it bigger, but let's say in this area here, the cleared area, this brown cleared deforested area, right? All of these swidden lines, let's say that all adds up to the same amount, 10 square kilometers. I would argue that this pattern of deforestation is much more destructive to the forest than simply taking out a rectangle or a square that is 10 square kilometers. So the question, Kylie, is why? Why would it be more destructive, do you think?
That's interesting because I thought the opposite. Like
Yeah,
I figured
right.
that more topography over a certain amount of like area would be better because then at least there's some trees. So, but I guess it impacts a larger amount of land and ecosystem.
Yeah, now you're thinking, love it. Okay, yeah, maybe it just, now I'm not for a minute arguing that this is great. By all means, Kylie, go in there and take out 10 square kilometers. Right? But from a species ecosystem standpoint, right, this one is actually more destructive. Why? Because you fragment the ecosystem here much more in the herringbone pattern than down below, right? And what we call that, the impact, then if you can read that, are what we call edge effects. The boundary or the edge effects are much greater here. Here's what I mean by that, right? If we were to take 10 square kilometers out of the bottom here, so this is, well, actually, let's make it 100 square kilometers. Let's keep the math easy. Let's say this is 100 square kilometers. Let's say it's 10 kilometers by 10 kilometers squared, right? Does everybody agree that 10 by 10 gives you 100 square kilometers? The boundary here, the edge between the intact forest and the cleared area is how long? It's 10 by 10 by 10 by 10. The edge here, the boundary, is 40 linear kilometers. Does everybody see that? Right? Let's say this area here, up here, is 100 square kilometers of cleared brown area, but the linear boundary, if you were to start going along and tracing all of this linear boundary, right, along the cleared and the uncleared, would be how much? It would be much longer than 40 kilometers. You may have an edge or a boundary here of several hundred linear kilometers. In other words, you've disturbed or fragmented the landscape. Now, just before I wrap up, getting back to Kylie's point, yeah, you might have some forest and trees in here, but that disturbs the species dramatically. It would be like going into a jigsaw puzzle and taking out 100 pieces in a square. You've cleared that square, right? And the boundary between your dining room table and the jigsaw puzzle around it is what it is. Or randomly going to the jigsaw puzzle and just taking 100 pieces out scattered across the jigsaw puzzle. Does that make sense to everybody? You are fragmenting, you're disassociating, you're slicing and dicing up the ecosystem and disturbing a much greater area, relatively speaking, in the slash and burn or shifting agriculturalists. Now that pattern of deforestation is not a global picture, right? This is just, I'm just kind of laying the groundwork here, leading, you know, so we can move from the Amazon into other parts of the world and look at other drivers. Does that make sense to everybody? Okay, cool. What's the time? Ooh, 55. Let's stop there. We'll pick this up tomorrow and talk about the reasons behind deforestation. Enjoy lab. Have a good morning, everyone.
Thank you.
You bet.
Thank you.
Thank you.
Thank you.
You bet. You bet. You bet. Let's see.